The next topic is coherent quadrature modulation techniques. These are bandwidth conserving schemes for the transmission of binary data. These are called the quadrature carrier multiplexing scheme because here there are two carriers cos 2 pi fct and sin 2 pi fct, and they are in quadrature with each other. The coefficient of cos 2 pi fct, this carrier, it is named as in phase component Si of t, and the coefficient of sin 2 pi fct carrier, it is named as Sq of t, which is a quadrature phase component. So the two techniques we are going to discuss here is, one is QPSK and there is MSK. QPSK stands for quadriphase shift keying. This is an extension of the idea of BPSK. In BPSK, we had the symbols as either it is a symbol 1 or a symbol 0. Here, the incoming binary data, it is grouped into 2 bits, and these 2 bits are called, they are named as D bits. We'll come to that later. In BPSK, there were only 2 symbols, so we need only 2 phase, 0 and pi, 0 and 180 degrees, to represent a symbol 0 or a symbol 1. Here in quadrature phase shift keying or QPSK, we have 4 values of phase that the signal can take. Those are given by pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. By observing, you can understand that adjacent phases, they differ by an angle pi by 2. The transmitted signal is defined as Si of t equal to root of 2e by t cos 2 pi fct plus 2i minus 1 into pi by 4 from 0 to capital T. In BPSK or BFSK, here I had named it as EB and ET, where EB stands for energy per bit and T was a bit TB was bit duration. Here we are grouping 2 bits. So those 2 bits is one symbol here. In BPSK, 1 bit was one symbol. Here 2 bits is one symbol. So E stands for the energy of symbol, energy of the transmitted signal, and T is the time duration of the symbol. Here the symbol consists of 2 bits, so 2 TB is the time duration. Si of t is given by this expression where I can take on values 1, 2, 3, 4. So we observe that as I vary from 1 to 4, in the transmitted signal, this is the factor that varies, and this is the phase. When I takes the value 1, this is pi by 4. I takes the value 2, we have 3 pi by 4, and so on. So each symbol, it is called a D bit. I have taken it as 1 0 0 0 0 1 and 1 1. These are gray coded symbols. Si of t, this expression, on opening this expression in the form of cos a plus b, we have this expression here. Certain observations we make from this Si of t expression is, there are 2 basis functions. One is root 2 by t cos 2 pi fct, other one is root 2 by t sin 2 pi fct. Second observation we make is, there are 4 message points. As a value of I vary from 1 to 4, there are 4 messages, and here vector Si, which is the coefficient of which consists the coefficients of basis functions phi1 of t and phi2 of t. Si is root e cos 2i minus 1 into pi by 4, which is the coefficient of cos 2 pi fct, and we have S12 as minus root e sine 2i minus 1 into pi by 4, which is a coefficient of sine 2 pi fct, which is the second basis function. The signal space characterization of QPSK. So we want to draw the constellation diagram containing the 4 possible message points. So we need to get the coordinates of the constellation diagram. The coordinates are the basis functions phi1 of t and phi2 of t. We need to get the coefficients si1 and si2. So as I vary from 1, 2, 3, 4, we have s1, s2, s3 and s4. So let us try to understand this. As when I has a value 1, the phase is pi by 4. Substituting that value here, s1 equal to root e cos pi by 4. Here it will be minus root e sine pi by 4. Root e cos pi by 4 is root of e divided by 2. Minus root e sine pi by 4 is minus root e by 2. So you have these values here. Similarly, symbol 0, 0 is when the value of I is 2. Substituting the value here, the value of I as 2, you get all these coordinates. So we are going to plot these coordinate points onto the constellation diagram. So in the constellation diagram, the coordinates are phi1 and phi2. We are plotting the first point corresponding to the symbol 1, 0, minus plus root e by 2 and minus root e by 2. So plus root e by 2 here, minus root e by 2 here. So the message point 1 is here at this point, debit 1, 0. Similarly, you can plot for all the other symbols, and always you will, after plotting, the phase will be given by this expression 2i minus 1 into pi by 4. How to draw the QPSK waveform? In order to draw the QPSK waveform, we need to split the incoming input binary sequence into odd and even sequences. So here the first 0, 1, 1 and 0, they are odd sequence. Here 1, 0, 0, 0, they stand for the even numbered sequences. From this table, we observe that if the incoming symbol is a 1, you have that coefficient as positive. For 0, you have it as negative. For 0, 0, it is negative and negative. For 0, 1, it is negative and positive. For 1, 1, it is positive and positive. So wherever there is a input 1, we put a positive sign. For a symbol 0, we put a negative sign. And we know our transmitted signal Si of t, it is Si1 phi1 of t plus Si2 into phi2 of t. Phi1 of t is the first basis function that is getting multiplied with Si1. And all these symbols, minus, plus, plus, minus, they are the signs of Si1. Here plus, minus, 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 all these are signs of Si2. As I mentioned here, Si1 and Si2 will contain these sign changes corresponding to the incoming bit is a 1 or a 0. That should get multiplied with phi1 of t. Si2 should get multiplied with phi2 of t. Phi1 of t is a cosine function, phi2 of t is a sine function. So here you have phi1 of t getting multiplied with a negative sign, so you have a negative cosine wave. It will be for a duration of 2 TB. Here you have a positive Si1. So you have the sine wave, positive sine wave. Similarly, below phi 2 of t is a sine wave. You have positive Si2 here, so you have the sine wave. Similarly, here it is a negative, so we have negative sine wave. And remember that this phi 1 or phi 2, they will stand for a duration of 2 TB. Why? Because these are odd numbered sequences and these are even numbered sequences. So the value comes only after 2 TB. After one odd sequence has come, the next value comes only after a 2 TB duration. Adding these two, you get the QPSK waveform here. This is the QPSK waveform. The disadvantage of this QPSK waveform is that there are positions where there is abrupt transition like this. This is a discontinuity which is not desired in a communication system. So this discontinuity may lead to non-linearities in communication system. So in order to overcome this disadvantage, we go for a technique called minimum shift keying, which will be discussed next. The transmitter of QPSK is fairly simple if you understand how this QPSK waveform is formed. So the incoming binary wave, it is split into odd and even sequence. Odd sequence gets multiplied by phi 1 of t, even sequence gets multiplied by phi 2 of t. The addition of these two gives the QPSK wave. In the receiver, the received signal is multiplied. This is a bank of correlators. There is one correlator here, the second correlator here. First correlator will give you the output x1, second correlator will give you the output x2, and then there is a decision device. Remember that this much part is same as your BPSK detection scheme. So here you have two carriers. You have two correlators here, phi 1 of t and phi 2 of t. So x1, if x1 is greater than 0, we decide in favor of symbol 1. x1 is less than 0, we decide in favor of symbol 0. Similarly for x2, then these two data, they are multiplexed, and finally you get the output binary wave.